Okay, good afternoon, everybody, and welcome. My name's David Gertis. I'm the chair of the physics department here at the University of Michigan, and it's my pleasure to welcome all of you to the Ford Lecture this year. All of you here in person, welcome to our viewers on the live stream, and especially welcome to members of the Ann Arbor community and beyond who have come here to celebrate this lecture. This lecture is made possible by a generous donation from the Ford Motor Company. We're very grateful for them. Are there any representatives or current or former employees of Ford in our audience today? Thank you very much for your support. Ford, of course, has been an incredibly important part of our identity as a state for well over 100 years and an important part of our present and future. So we really appreciate their support for physics in our department. I'd like to recognize a couple of special guests in our audience today. Larry and David Lineweber are with us. Their generous gift endowed the Lineweber Center for Theoretical Physics that supports a great deal of work in fundamental physics in our department. So thank you for being here. I also want to point out that our speaker, Professor Carroll, has generously agreed to extend his stay by a day and give our Saturday morning physics talk tomorrow. I see a lot of regulars in our Saturday morning physics audience in attendance here today. So if you like this talk and you want to hear more, or if you hate this talk and you think the guy deserves a second chance, that talk will take place starting at 10:30 over in Weiser Hall. And you can, the title is The Many Worlds of Quantum Mechanics. And you can learn more about that by going to SaturdayMorningPhysics.org. One more detail before I introduce the person who will introduce the speaker. After the talk, there will be time for Q&A, and you'll notice there's a couple of microphones there. So if you are able to do so, you can line up at either microphone. And if you are unable to do that, please raise your hand, and we have some students who can meet you at your seat and give you a microphone. But in any case, please wait for a microphone and then be acknowledged to ask your question. So now it's my pleasure to introduce my colleague, Fred Adams. Fred is the Taya Wu Collegiate Professor of Physics and Professor of Astronomy here at the University of Michigan. He works in the same general area as Professor Carroll, and he will introduce our speaker. Go ahead, Fred.
Okay, good afternoon, everybody. It's a great pleasure today to introduce Sean Carroll. Sean is the Homewood Professor of Natural Philosophy at Johns Hopkins University in Baltimore. He's also on the fractal faculty at the Santa Fe Institute. I'm not sure what that means, but if he slowly dissolves before your eyes, don't be alarmed. He will come back. Sean has had a very long history of working on a lot of different topics in physics, astrophysics, and recently philosophy. He started at Villanova, I guess, and then he did his PhD with George Field at Harvard. After that, he went to MIT for a postdoc, and then the Kavli Institute for Theoretical Physics at UC Santa Barbara for another postdoc, and then came to our neighborhood where he was a professor at the University of Chicago for a while. He then moved up to Caltech as a research professor, where he stayed from about 2006 to relatively recently in 2022, and then he moved to Hopkins, where he is now. Now, over the course of this journey, he's worked on a wide variety of different topics, including space-time symmetries, dark energy and dark matter, and especially the cosmological constant, which is a subset of that, modified gravity, the arrow of time, foundations of quantum mechanics, and the actual emergence of space-time. Now, if you know, these research topics kind of butt up against the edge of what's physics and kind of borders into what's most people consider as philosophy, so it makes a lot of sense that he is now at least partly associated with philosophy. Now, I also note that along the way, in addition to his physics and intellectual or academic intellectual contributions, Sean has done a lot of other things. He has written 7 books. He has written almost 100 popular articles. He's been on television and consulted for television and film, including Thor. And he's given TED Talks, and on it goes. So I won't list the whole thing in order to actually give him some time to give his talk. But I would like to note one thing, that Sean is one of the very few scientists who have actually successfully made the transition from just a mainstream academic scientist to a very successful public intellectual. And even more rare than that, he's managed to do so while continuing to keep an active fully active research program going. So he's one of very, very, very few people that can get away with that. So we're very lucky to have him here today, and we look forward to his talk, which is on the secrets of Einstein's equation.
Thank you, Fred. Thank you, David. It's great to be here. Even though Wolverines and so forth, I'm a Penn State Nittany Lion fan, Big Ten rivals. What can I tell you? But in a few weeks, we'll settle all that. In the meantime, we can be collegial and friendly. This talk is a slightly unusual one. You know, if you mostly go to popular level physics talks, they will tell you about the most recent cool discovery or even speculation, right? We found gravitational waves. Maybe there's a multiverse, something like that. Whereas if you take an introductory physics class as a non-physics major, they'll teach you the simplest stuff, like here's a ball rolling down an inclined plane. And it's hard to find the in-between. So that is what I'm here to tell you about. It's not speculative. Einstein's equation is over 100 years old now. But the trick is, this is a talk for everybody. There are no prerequisites, but I'm going to do the math. There will be math in the talk. And then afterwards, there will be a take-home exam where you can hand it back to me over Canvas. I don't know, do you use Canvas here? So, okay, good. And we'll get some volunteer graders. So we'll see how that goes. Now, maybe you think you know Einstein's equation is kind of famous, right? E equals mc squared. And it's, despite Einstein's reputation, E equals mc squared is not that hard to understand. It's a multiplication of m times c, and then c is squared, but you can get that. Energy of an object at rest is the object's mass times the speed of light squared. How hard can it be, really? But this is not what physicists mean when they say Einstein's equation. This is what physicists mean when they say Einstein's equation. This says r mu nu minus 1/2 r g mu nu equals 8 pi g t mu nu. Now that seems kind of hard. There's subscripts, they're in Greek. I don't know what any of the symbols mean. By the end of this talk, you will know what all of these symbols mean. And the reason why this is what physicists call Einstein's equation is because this is the equation that explains how gravity works. You may have heard that Einstein said gravity is the curvature of space-time. This is the equation that embodies exactly what that says. There's many people here in the physics department, many of whom I was talking to earlier today, that spend their time solving this equation. So now you'll be able to hang with them and help them solve it or something like that. At least you'll know what the symbols mean. To get there, I did say that this is for everybody, so we start slowly. The idea of classical mechanics. This whole talk is what we call classical in physics, if you want quantum mechanics. Tomorrow morning is the talk for you, but today we're going to be strictly classical. This is a paradigm for doing physics that was handed down to us from the time of Isaac Newton and his friends. And there, the really important equation is Newton's second law of motion, F equals ma. Force equals mass times acceleration. And again, this equation has the feature that it's not that hard to understand, right? There's only one multiplication in there, m times a. Mass times acceleration is force. The only slightly tricky thing is that there are little arrows on top of the F and the A. This is reminding you that these are vectors, which is to say both force and acceleration have a direction in space as well as a size. But other than that, it's very straightforward. The more you want something to accelerate, the more you push it. And the direction in which it accelerates will be the direction in which you push it. So here's an example of pushing something. Cars do not start all by themselves. You have to push them, either from inside or outside. I know the picture is kind of small, but there's a little puppy dog driving the car. I don't know how realistic that part is, but the pushing part makes perfect sense. Why is this equation of Newton's so important? Why do equations show up so ubiquitously in physics? Number one, because it's precise, by which I mean it's not just a suggestion. It's not like saying things roll downhill, right? This is a precise quantitative relationship, and that's what you need if you want to get a rocket to the moon. If you want to get a rocket to the moon, you don't need quantum mechanics. You don't even need general relativity. this equation plus Newton's law of gravity is more than enough to do the job, but it had better be very, very precise. The other aspect is that it's everywhere. It's universal. And this is really what made Newton his money. This equation is supposed to be true, not just for some particular force that you act on some particular object, but for every time any force is exerted on any massive object in any situation whatsoever. It is amazing that there exist equations like this. If you want to know why equations are so important to physics, it's because they're compact and precise, but also they apply over and over and over again. There's an extraordinary amount of power in these equations. In a very real sense, they are smarter than we are, and we will see that at work. So to put this to work, force equals mass times acceleration, you have to tell me, well, how much force is being exerted? So the other famous equation Newton wrote down was his equation for gravity, the famous inverse square law. If I have two objects, capital M for some heavy object, little m for some little object, a feature of these equations is it doesn't matter what letters you use. You could use Y and Q if you wanted to, but it's nice to use letters that vaguely remind you of what you're talking about. So capital M for a big heavy mass, little m for a little mass. And this equation right here tells you that the force being exerted by the big mass capital M on the little mass little m is the product of their masses, m, times a constant of nature, capital G, Newton's constant, divided by the distance between them squared. That's why it's the inverse square law. So if two objects of a certain mass are very close, the gravitational pull is relatively big. As they get further away, the gravitational field is weaker. And so once again, there's arrows, and there's a little E, which is just the direction between the two objects. So it's telling you in what direction the gravitational force is pulling you. This story of Newton seeing an apple fall from the tree was a very early example of what we would now call disinformation. This was a story spread by Newton himself because he thought it made him sound cool. The idea was not that no one knew that apples fell down from trees, or even that gravity caused it. Newton's insight was that the same law of gravity could account for apples falling from trees and for the motions of planets around the sun. It's that universality, that everywhere quality of equations showing up once again. And we can even take these two equations, F equals ma and F equals gmm over r squared, and do math with them. So we're ramping up quickly, okay? So both of these quantities equal the force, so we set them equal to each other, and a miracle occurs. We notice that in the expression ma, the mass of the little object times its acceleration, and the expression gmm over r squared, there's a little m that we can cancel out. So let's do that. And we get a new equation. We've just done some math, and we get an equation that just tells us the acceleration of an object, and the acceleration of an object in a gravitational field points toward the gravitating object and depends on the mass of that object, Newton's constant, and the distance, 1 over the distance squared. This is an amazing fact that we just derived, and you can see why the equations are kind of fun, because you can get a consequence by pushing them around. And in this case, the consequence is gravity is universal. If I have an electric field in the room, and I have a positively charged particle and a negatively charged particle, they will move differently. One will move in one direction, one will move in the other. But the mass of the little particle that is basically the gravitational equivalent of its charge doesn't appear in this equation for the acceleration. No matter what the mass of the object being pulled on is, it will accelerate in the same way according to the force of gravity. So for example, if you have a feather and a hammer, a light object and a heavy object, if you drop them, if you asked a regular person which will fall faster, they will say the hammer. If you ask a physicist, they will say they fall at the same rate. Now, the regular person is correct in this instance because there is such a thing as air resistance in the world, and physicists don't believe in air resistance. They zero it out in their minds. But if you do the experiment on the moon, which was done by Apollo astronauts, then indeed, the feather and the hammer fall at the same rate. This is a feature of the gravitational force. It is unlike any of the other forces. That fact about gravity, the fact that it is universal unlike any other force, will be important early on, later on. But this overall picture works very well. It was so good that if you were a 19th century physicist, you would basically have believed that we were pretty close to figuring everything out, to fully understanding the laws of nature. They were not right. One of the ways in which they were not right was summed up by this guy, Albert Einstein. You're often shown pictures of Einstein in his later years, when he was a little rumpled, the hair was out of control, the sweaters were not often washed. When he was a young guy, when he was inventing these equations, he was a sharp-dressed young man, and smarter than everybody else. So his achievements in 1905 are multiple. He wrote many papers, any one of which would have made the career of a regular scientist. One of the more memorable ones was the theory of special relativity, where he says that motion is relative. There's no absolute standard of rest by which I can say I am rest with respect to the universe or anything like that. But the speed of light is constant. These two facts, motion is relative, but the speed of light is not relative. The speed of light is the same for everybody. These are very, very hard to reconcile, and people had noticed this and struggled with it for decades. Einstein's great insight was really to say, you need to change how you think about space and time, how you think about the time measured by clocks, the distance measured by measuring rods or something like that. These are what leads to length contraction, time dilation. There's a usual set of phenomena that are explained when people talk about special relativity, none of which I will talk about, because we're going to do things in a slightly different way. But this wasn't quite the final word on special relativity. We're distinguishing between special relativity, which is the theory that starts by saying motion is relative, the speed of light is constant. General relativity comes 10 years later, and that's the theory of gravity. So this theory didn't yet have gravity. And the finishing touches were actually not put on by Einstein, but Einstein's former university professor, Hermann Minkowski. In 1907, Minkowski was a geometer. He was a mathematician. And Einstein was not a mathematician. He was very good at math, don't get me wrong, but he only ever used exactly the amount of math he needed to do his physics. He really cared about physics. Whereas Minkowski was a geometer, a mathematician through and through, and he figured out that the most beautiful, elegant way to conceptualize Einstein's theory of special relativity was as a unification of space and time into a four-dimensional thing that we call spacetime. The famous quote is, henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. They don't write physics papers like that anymore. They don't write math papers like that anymore either. But despite the beauty of the conception, not everyone was impressed. For example, someone who was not impressed, Albert Einstein, who said that Minkowski's formulation makes rather great demands on the reader in its mathematical aspects. So you imagine, like, Einstein is complaining that your theory is too mathematically challenging, you might have second thoughts. It turns out, as often happened in his career, Einstein was wrong about this, and among his many, many good qualities, Einstein was super good at changing his mind. When he realized that something was actually a good idea after all, he did not hesitate, and he soon adopted this geometric space-time point of view. So why? Why is it useful to think of special relativity as a theory of space-time, and in particular of the geometry of space-time? All those things we talked about, length contraction, time dilation, they all come down to the fact that space-time has a kind of a different geometric character than the ordinary geometry we know and love. So here's the ordinary geometry we know and love, Euclidean geometry, the geometry of a tabletop or a flat surface, or for that matter, a flat three-dimensional plane. one of the famous results of Euclidean geometry is Pythagoras' theorem, right? Do you remember Pythagoras' theorem? Anyone remember it fondly? I don't know if I'm scaring people or bringing up bad memories, but it's a pretty simple thing. If you have a right triangle, a triangle with a right angle, you have a long side, the hypotenuse, two shorter sides, and Pythagoras says the length of the long side squared is the sum of the lengths of the shorter two sides, also both squared. So if you have, let's say, coordinates, right? If someone goes and builds a grid on the ground and labels one direction X and the other direction Y, and you have 2 points on the grid at different values of X and Y, Pythagoras' theorem gives you a way to calculate the distance between those 2 points. Take X, take Y, add up X squared and Y squared, and you get the distance squared. So the distance itself is the square root of that. So if you're literally measuring the distance that you're traveling, this is supposed to be a guy with an odometer, right? He's counting his steps. So he's measuring his distance. You could, instead of using an odometer or a step counter, you could use Pythagoras' theorem to figure out how much you have traveled. The entirety of special relativity consists of 2 statements. One is space-time is like that, is kind of like space, but the second statement is there's a minus sign that comes in. So in other words, if you have 2 events in space-time rather than points in space, by an event in space-time we mean a complete specification of where you are in space and when you are in time. If you're told there's going to be a lecture, you need to be told what time it is and where it is, right? If you're only given one of those pieces of information, you're not going to find yourself there at the right time. So an event in the 4-dimensional space-time is both where and when. And I could also set up a coordinate system on space-time. I could have X telling you how far away it was in space, T telling you the difference in the time coordinate. And Minkowski says the way to think about this is the difference between special relativity and Newtonian mechanics is that the time coordinate that we all use to say, be at the lecture at 4 p.m. or something like that, is not the amount of time that your clock measures. The amount of time that your clock measures is like the distance along the hypotenuse of the triangle. It depends on how you travel. It depends on how you move through space-time, and the dependence is very easy to summarize. If you move on a straight line in space-time, the interval that you measure on your clock, let's call it tau, our first Greek letter of the day. It will not be our last Greek letter. We like the Greek letters. So we're distinguishing between the time coordinate t, that is universal and everyone agrees on, versus tau, which is what I personally measure on my wristwatch. And there's a formula for tau, which is that tau squared equals t squared minus x squared. So what this is saying is, the more you move in space, the more x that there is, for any given amount of motion in t, the less time you experience. You may have been told the story of the twin paradox. One twin stays behind on Earth, one zooms out in a spaceship near the speed of light and comes back. They don't have to be twins. They're just more dramatic if they're twins because they're the same age. But when they come back, they're not the same age. And you may have struggled to remember which one was older and which one was younger. This minus sign tells you the answer to that. The more you move in space, the less time you experience. The twin that stays behind stationary on Earth will be older than the twin that zooms out near the speed of light and comes back. A tiny little change in the equation with enormous physical consequences. So this is the sense in which special relativity is a theory of the geometry of space-time. It's like Euclidean geometry, but different, Minkowskian geometry. All very well. Einstein eventually reconciled himself with his fancy pants mathematics, but he was struggling with another problem. The very first thing we did when we talked about Newtonian mechanics was to say, okay, F equals ma, force, I like that. What's a good example of a force? Gravity. So since Einstein had changed the nature of mechanics with his theory of special relativity, of course he would want to fit gravity within that new context. There was also electricity and magnetism as put together by Maxwell in the mid-1800s, but that was prearranged to fit well with special relativity. Special relativity was basically built around making sense of electromagnetism. Gravity didn't fit very well. So Einstein realized he would have to come up with a better theory of gravity to be compatible with relativity. And his starting point was, because Einstein, I make a joke about his ability to change his mind, his real genius was the perfect thought experiment. He could put his finger on exactly the physical phenomenon that we would have to concentrate on, and then he would resign himself to doing the math for it later, but he could do it. And he realized that the secret lay in that realization we had that gravity is universal, that everything falls the same rate in a gravitational field. If you want to detect the existence of an electric field, give me a charged particle, a positively charged one and a negatively charged one. I can see how they're moving differently, and I can tell you how much electric field there is. But Einstein says, because everything falls at the same rate in a gravitational field, you think here in this room, there's a gravitational field, because you're being held into your seat by the gravitational field. But Einstein says if there were no gravitational field here, and instead this room was in a spaceship that was accelerating upward very quietly at 1g, you would not be able to tell. There's no experiment you can do here in the auditorium that can distinguish between being in a gravitational field and just being accelerated. That is entirely different than every other force of nature. So Einstein, again, being Einstein, said, I know what to do with this. The lesson to learn from this is that gravity isn't like the other forces. It's not a force living on top of space-time, pushing different kinds of particles in different directions. It's a feature of space-time itself. That's why it's universal. That's why everything is affected by it in the same way. What feature is it of space-time? It's the curvature of space-time, the geometry. He had learned from Minkowski that space-time has a geometry, and the geometry was a pretty simple generalization of Euclidean flat tabletop geometry. But earlier in the previous century, mathematicians had worked out that there were other kinds of geometry with curvature in them, and Einstein had the brilliant idea that maybe that curvature could help him explain the force of gravity. Sadly for Einstein, he knew nothing about all this fancy mathematics, dealing with the curvature of different mathematical spaces. Happily for him, his friend did. Marcel Grossmann was one of his buddies from a university who had become a mathematician, played a crucial role in the development of general relativity. He taught Einstein the geometry, the mathematical tools that he needed. Still one of the major general relativity conferences is called the Marcel Grossmann meeting. Without Marcel Grossmann, the history of general relativity would have been completely different. So Einstein gets tutored. This is, years after he wrote all of his Nobel Prize winning papers. So you still need tutoring. It doesn't matter what stage you are of your life. And here is what he learned. There's this thing called Euclidean geometry, which is what we learn in high school, tabletop geometry. But there was always, since the time of Euclid, a little bit of a lingering mystery about Euclidean geometry. Euclid was famous he didn't invent most of the geometrical theorems. What he did was express the rules of geometry as a set of axioms or postulates from which the theorems can be derived. And most of those axioms were pretty straightforward, hard to argue with, but one kind of stuck out as a little tricky. It's called the parallel postulate. The idea is that I have a little line segment, and from it I shoot off two lines initially parallel at right angles to the initial segment. They will always stay the same distance apart. They always remain perfectly parallel. This is very intuitive. It just makes sense. So much so that for years, mathematicians tried to prove it on the basis of the other axioms. I don't know about you, but my junior high school geometry teacher tortured us by offering extra credit if we could prove the parallel postulate of Euclidean geometry, many of us tried, none of us succeeded because you cannot prove it, because it is not necessarily true. And this was finally figured out in the 1800s by the introduction of other forms of geometry. You could replace the parallel postulate with a different postulate. You could say that two initially parallel lines might gradually come together and converge. In that case, you get spherical geometry. The surface of a sphere has this property. You start two lines at the equator, two lines moving perpendicular to the equator are just lines of longitude, and they're going to hit each other at the North Pole. Or you could have two initially parallel lines diverge from each other, and that's like living on the surface of a saddle or a potato chip. That's now called hyperbolic geometry. So this was all great. People became famous, early 1800s, new foundations of geometry, very, very exciting. But there is a hidden assumption in all three of these geometries, and sometimes in short histories this will be glossed over. But the hidden assumption here is that the amount and character of the curvature, where there is curvature, is exactly the same everywhere. There is either a uniform convergence or a uniform divergence of those initially parallel lines. From that assumption, you derive that it's a sphere or it's a saddle or whatever. But look, once you've opened Pandora's box and you have spheres and saddles, you can have any old sort of thing. They don't need to be two-dimensional. You could have three-dimensional or 29-dimensional spaces if you want. They could be curved positively somewhere, negatively elsewhere. There's clearly a lot of generalizing to be done. This is what mathematicians are good at. So the first person to take it up seriously was Bernard Riemann. Actually, the first person to take it up seriously, this challenge of arbitrary geometries, was Carl Friedrich Gauss, one of the greatest mathematicians of all time. For whatever reason, he didn't quite finish the job, and Riemann was his graduate student. And in the German system, you never stop writing theses. Like, you just got to keep writing new papers to get higher and higher up the academic ladder. And at one point, Riemann was also already a pretty accomplished mathematician, but he had his one more degree to get in order to be allowed to teach in universities. He went to Gauss, who was his thesis advisor. He gave him a list of topics he'd be willing to write about. Gauss told him to write about the one that Riemann thought was the most boring one, the foundations of geometry. And he actually, in the course of writing this book that I'm talking about here, I actually looked up Riemann's original paper, something we never do, right, as working physicists. And you see Riemann kvetching throughout the paper, like, I don't like doing this, this is not my style, if you force me to do it, I guess I will do it. His job was, what if the geometry of space is different from point to point, from direction to direction, in multiple dimensions, without taking advantage of embedding your space in some bigger space? We want the intrinsic geometry of a space itself. And the starting point is to say, like, how would I even keep track? What are the data? What are the pieces of information that would tell me what the geometry of a space is? And Riemann's single brilliant insight, a lot of what you learn now in your graduate level geometry or differential geometry or general relativity course under the name of Riemannian geometry, was developed by completely other people after Riemann. He set the stage, and then he unfortunately passed away at a pretty young age. But his brilliant insight was, just tell me the length of any curve that I can draw. If you tell me the length of a curve, I can figure out anything from that. So let's say you have a surface, I want to get the area. I could, in my mind, slice up that surface into a lot of little lines, calculate their lengths, and then I would know the area. The length of an arbitrary curve tells me everything I need to know about the geometry. And what is that? How do I tell you the length of every curve? Well, by this time, they knew a little something called calculus, which means you zoom in on an infinitesimal region, give me the information there, and then I build it up bit by bit. So in flat space, for example, Riemann would tell you to zoom in on some curve. You have some wiggly curve through space. You want to know its length. And Riemann says, just zoom in on it. And if space is flat, then I know a formula for the length of an infinitesimal curve. It is called Pythagoras' theorem. It's the generalization of Pythagoras' theorem to multiple dimensions. So if you have 3 dimensions of space, for example, the interval, the length of that curve, squared, is going to be x squared plus y squared plus z squared, rather than just x squared plus y squared, but that's the same basic idea. Riemann's task is to generalize this idea, to come up with a way of telling you in a simple, concise, compact formulation what is the length of any infinitesimal curve. And from that, everything follows. So how do you do that? You want to generalize Pythagoras' theorem. Pythagoras tells you how to do it in flat, 2-dimensional space. How do I do it in arbitrary numbers of curved dimensions? So the answer, I'm just going to tell you the answer. You're going to believe me. I'm pretty sure you're going to believe me. You should believe me. It is the correct answer. The answer is, if you stare at this formula, d squared is x squared plus y squared. We have on the left some interval squared. On the right, we have our coordinates, x and y, and we've taken pairs of coordinates and multiplied them together. And then we've multiplied that pair of coordinates by some number. In particular, in the case of Pythagoras' theorem, we've multiplied x by itself and multiplied that by 1. So we get x squared. Then, secretly, you didn't know, but we multiplied x by y. But we multiplied it by 0 then. And we multiplied y by x and multiplied that by 0, and multiplied y by y and multiplied that by 1 again. You can see like the process of generalization. Pythagoras' theorem is very simple and elegant, but if we want to make it more complicated and ugly, we have to allow ourselves to include a whole bunch of extra things that disappear in the simple case. So these 2 equations on the slide right now are, of course, the same equation, right? The second one says d squared equals 1 times x squared plus 0 times xy plus 0 times yx plus 1 plus y squared. But it has the nice feature that you can kind of see how we're going to go about generalizing it even more. In space-time, for example, where you have not just x, y, z, but t, x, y, z, the time coordinate, the general formula, Minkowski's formula fits into this paradigm, right? Tau squared is t squared minus x squared. So it's kind of like Pythagoras, except the coefficient is now minus 1 instead of plus 1. Whereas in general, you're going to have some number times t squared, some number times t times x, some number times t times y, plus blah, 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 all the way down. It gets very tedious, very, very quickly. Nothing brings more joy to the mathematician than the ability to take a complicated expression and invent new notation to make it look really simple. So let's do that. We're biting the bullet here. We're following our noses. This is going to lead us to a beast called the metric tensor, g mu nu. So what we're going to do is, rather than writing out the coordinates on space-time, t, x, y, z, we're going to label them with numbers. x0, x1, x2, x3. Why does t get the 0th coordinate? Because somehow they knew that down the road, nature would give rise to string theorists. And they would talk about like 10 dimensions or 26 dimensions or whatever. There's always one time dimension and some extra number of spatial dimensions. So it's just very convenient to call the time coordinate x0 rather than x4. I don't know how they knew that. It worked out quite well. Also, this is a little trickier, but x1 and x2 and x3 do not mean x to the first power, x to the second power, x to the third power. This is just a failure of different kinds of notation. This means the first x-coordinate, the second x-coordinate, the third x-coordinate, the 0th x-coordinate. And even that is kind of tedious, so we're going to take those numbers, 0, 1, 2, 3, and give them the index mu, the Greek letter mu. You see our Greek letters coming back. They were mu's and also nu's on the very first slide when we saw Einstein's equation. This is where they come from. They're labeling coordinates in space-time. There's nothing scary about it here. X mu, for different values of mu, is just time, x, y, z, things you've seen many times before in your life. And then, rather than saying a times t squared plus b times tx, etc., we ask ourselves, what is the number in the distance formula that multiplies the x muth coordinate times the x nuth coordinate. We're going to call that g mu nu. So this is a little scary, but here's what we get. The space-time interval, the distance in space-time between 2 points squared, is some number times x0 squared plus some number times x0, x1 plus some number times x0, x2, etc. And that number is g0, 0 times x0 squared, g0, 1 times x0, x1, etc. Still not bringing joy to the mathematicians who don't like ugly notation. So if we call these indices mu and nu, this all collapses. And all we're really doing is writing a sum over all possible values of mu and nu of some coefficient g mu nu times the two coordinates x mu and x nu. Pretty compact. This is the generalization of Pythagoras' theorem. And in fact, even this is slightly annoying. Because you know you're going to sum over mu and nu. Why do you have to keep writing that big Greek letter sigma? That's the summation sign that mathematicians use. This just means sum over all the values of mu and nu. This is a big problem for mathematicians that was solved hilariously by Albert Einstein. And Einstein said, I know what to do. Whenever there's a sum over mu and nu that appears twice on the right-hand side, don't write it. Brilliant. He actually joked in a letter to a friend of his, I have made a great discovery in mathematics. You do not need to write the summation sign. And this is called the Einstein summation convention. So instead of Pythagoras' theorem, d squared is x squared plus y squared, in a general space or space-time, we have interval squared is g mu nu x nu, with an implied summation over all those values. Whew. So this is an enormous step forward in terms of compactness of notation, hopefully not a step backward in physical understanding. So let's think about what is going on here. So let's go back to Minkowski space. Minkowski says space-time is kind of like space, except there's some minus signs in front of the spatial coordinates. So what that means in practice is that the time you read on your watch, tau, obeys this equation. Tau squared is t squared minus x squared minus y squared minus z squared. We're going to write exactly that in terms of the metric tensor g mu nu, right? So g mu nu, in principle, has a g0, 0 or equally well gtt, doesn't matter, just labels, right? The thing that multiplies x0, x0, which is the thing that multiplies t squared. And that, if I compare to this formula, had better be plus 1. Whereas there's no appearance in this formula of x times t. That's okay. That just means that gtx is 0. And so on down the line. So what you have in this formula is a set of spatial distances, the formula for just the distance in space. Forget about space-time. Part of the distance between two events in space-time will be the spatial part. That's what this part of the metric is doing. Another part is, this is tricky, the rate at which time flows with respect to the time coordinate. So once you're in the world of relativity, there's the time you read on your watch. There's also a time coordinate you put on the universe. Those two things can have an arbitrary relationship to each other. But you want to be able to calculate what that relationship is. Here it is. It's the 0, 0 or the TT component of the metric tensor. And then these other ones, time times space, is literally representing time and space twisting into each other. And you might say to yourself, I have never seen time and space twisting into each other. What is that all about? But I can predict with, I bet, at least 80% accuracy that you have seen time and space twisting into each other. Here is a picture of it. Anyone know what this is a picture of? It's the black hole image from Interstellar, the movie. Christopher Nolan, Matthew McConaughey, you know what I'm talking about. So Kip Thorne my former Caltech colleague, Nobel laureate, and executive producer of Interstellar, worked hard with with various people in the special effects shop that was assigned the task of making the black hole for the movie Interstellar to really figure out how it would work. A black hole in nature, there's a black hole at the center of our galaxy several million times the mass of the sun. People who work on gravitational waves see black holes spiraling to each other all the time. Black holes exist, and they tend to be spinning very fast. That spinning of the black hole warps space and time into each other. You cannot describe a spinning black hole without including those green parts of the metric right there. And it was so much work that they literally wrote a paper in a physics journal. And if you look at the affiliations of the authors, Kip Thorne is last. The other three work for the special effects team, Double Negative Limited in London. And this was published in Classical and Quantum Gravity, which is a semi-respectable gravity journal. So it's important that space and time can twist into each other, something that general relativity allows for and Newtonian gravity never did. So now we have the tools in hand to really roll up our sleeves and do some math, finally. That was a joke. We've been doing math all along. So Riemann tells you that if you know the distance along any infinitesimal curve, in principle you can work everything out about the geometry of a space. And it's the metric tensor that tells you the distance along any infinitesimal curve. So, okay, let's work out some of the geometry of a space. Let's just ask the simplest question. Is the space flat or is it curved? The tricky part of that question is there's only one way to be flat, but there's many ways to be curved. Positively curved, negatively curved. Maybe it's positively curved in this direction, but negatively curved in that direction if you have more dimensions of space. Not to mention space-time. So what we're going to need is another tensor. A tensor, don't worry about the tricky definition. It's just a collection of numbers arranged into an array. The metric tensor is a 4x4 array of numbers. The Riemann tensor, oh my goodness, 4 different indices. R, lambda, rho, mu, nu. You can calculate it. When I was your age, we calculated the Riemann tensor with our fingers. Now you just ask the computer to print it out for you. But there's a formula that gives you the Riemann tensor from the metric tensor. And the Riemann tensor you can think of as the answer to a question. How curved is space or space-time at any one particular point? And the way it answers it is by going back to Euclid and saying, if space were flat, the parallel postulate would be true. So 2 initially parallel curves would stay exactly parallel. Therefore, what I mean by curvature is a failure of initially parallel lines to stay parallel. So if I start 2 initially parallel lines and I plug them in to the Riemann tensor for some space or space-time that I have under consideration, the Riemann tensor tells me how they are moving apart. Not only are they stretching or contracting, but also could they twist past each other? What direction did you start them in initially? The whole shebang. So all the possible forms of curvature are encoded in this unwieldy beast we call the Riemann tensor. Just to hit home how unwieldy it is, whenever you see an index on a tensor in relativity, that's running over the indices of space-time. That's what it does. Every mu, or every nu, or every rho, any one of these Greek letters is either 0, 1, 2, or 3. If you are in 10-dimensional space-time, bless your heart, you got some work cracked up for you, but let's stick with 4-dimensional space-time. So something like the momentum in space-time is a vector. It has 4 components, pt, px, py, pz. Something like the metric tensor is a tensor, has 2 indices, so it's 4x4, 16 components. There they are. The Riemann tensor is a 4x4 matrix of 4x4 matrices. So 256 components. Please don't tell me you see a typo in this expression. It was a certain amount of effort. I did it for you. This is completely useless, this expression. No physicist ever writes it down like this. All I'm trying to convey is there's an enormous amount of information contained in the Riemann tensor, all of which can be derived from the metric tensor, so it's a nice little structure. And I know that was a lot, so let's catch our breath and remember why we were doing this. The point is, Einstein says space-time can be curved. It's not going to be as simple as a sphere or a saddle or something like that. It can be curved in all sorts of different kind of ways. It can be arbitrarily complicated. What Riemann tells us is that you can encode that curvature in the length of every infinitesimal curve. And specifically, that information is encoded in the metric g mu nu, from which you can derive the Riemann tensor, which tells you the curvature. So those are the mathematical tools we have to work with. Metric and curvature are supposed to help us in our task, which, remember, is to construct a theory of gravity. So what to do about that? Well, Einstein knew this one. This is Newton's equation for the acceleration due to gravity. Remember the equation where we canceled out the little m's? So we get an acceleration that depends on stuff, right? Masses and distances between them. So Einstein needs a generalization of this to gravity and curved spacetime. So the task is to replace acceleration with something that depends on the curvature of spacetime, and to replace the mass of the object causing the gravitational field with some general relativity version of that. Because you know it's not going to be as simple as the mass, because you know that Einstein previously wrote down E equals mc squared. There's a unification in relativity of energy with mass. And frankly, it goes a lot further than that. There's a unification of momentum and heat and pressure and strain, all those crazy things. Relativity provides a single unified way of talking about that mass energy-like stuff. What kind of mathematical structure should we use to describe this complicated thing? A tensor is the answer. And we'll call it, unimaginatively, the energy momentum tensor. Some people call it the stress energy tensor, not a big deal. The point is, it's another two-index tensor, T mu nu. So there's TT coordinates, TX components, etc. And just like the metric, we can tell you what all these mean. The TT coordinate of capital T is basically the energy of the system, which includes the mass. So what Isaac Newton would have cared about is up there in the corner, the 0, 0 or TT component of the energy momentum tensor. The diagonal, the other diagonal components in the spatial directions are the pressure. So we're now imagining, remember, we're trying to be completely general. So if you're at the center of a star, you don't just have a point, you have like a whole continuum of stuff around you. So there will be amounts of pressure in different directions. We now think that the universe is full of dark energy, which has a negative pressure. And this is all sitting there in the energy momentum tensor. The x component is the amount of pressure in the x direction, and so on. All the other energy-like things, the momentum, the heat flow, the stress, and so forth, are bundled up in the off-the-diagonal elements of this tensor. You don't need to follow. You don't need to care about what specifically they are. All you need to know is the structure, the expression that tells you energy and mass and all that stuff is a two-index tensor called the energy momentum tensor. So what Einstein is left with is a metric that tells you the Riemann tensor, and then separately energy and momentum given by another tensor, and he's supposed to use this to construct a replacement for Newton's theory of gravity. There's an instant problem. I said on the left-hand side, you need something that has to do with space-time curvature. On the right-hand side, you need energy to match what Newton said. But space-time curvature is expressed by a tensor, the Riemann tensor, with 4 indices. On the right-hand side, the energy and momentum is expressed by a tensor with 2 indices. Those are not the same number of indices. You can't set them equal or proportional or anything like that. You are in trouble. There's an obvious problem. Happily, this is an obvious problem that the mathematicians had already worked out. There's a whole bunch of Italian mathematicians who were just really into non-Euclidean geometry in the 19th century. And what they figured out, there is a way of distilling down the important parts of the Riemann tensor to other tensors with fewer indices. So you have the Riemann tensor with 4 indices, and you can take sums of different components to get something called the Ricci tensor with 2 indices. And you can keep going to make something called the curvature scalar with 0 indices, just a number at every point. Now you might think, aha, I know what to do, because what you want to do is to set a tensor that is characterizing the curvature of space-time proportional to the energy momentum tensor T mu nu that has 2 indices. Look, there is a tensor right there, the Ricci tensor, that also has 2 indices. In fact, there's other nice properties that it has that matches up with the energy momentum tensor. So you might guess, or hypothesize, as we would say, that there is a relationship that relates the Ricci tensor to the energy momentum tensor. If you did guess that in the last 30 seconds, congratulations, because you and Einstein both. Einstein also suggested that. It turns out not to work. It doesn't work because then energy and momentum would actually not be conserved in this theory, which would be bad for different reasons. That's a whole other talk. But you also have this curvature scalar, you also have the metric tensor, and Einstein was clever enough to come up with a combination of those 2 things that does work. And this is the equation that we started with. R mu nu minus 1/2 R G mu nu, so the Ricci tensor minus a half curvature scalar times the metric is proportional to the energy momentum tensor T mu nu. The right constant of proportionality works out to be 8 pi g, where g is Newton's constant. So this is Einstein's equation for the curvature of space-time in general relativity. Now you know what all those symbols mean in the equation that we started with on the first slide. So that's one good news. Now there's bad news. What you do with an equation like this, when you're a physicist, is you solve it. Or you assign it to your graduate students to solve it when they take your class. This equation is really hard to solve. There is a miracle of notation. Sometimes physicists find it slightly tiresome to write out the whole left-hand side, so they call it the Einstein tensor, capital G mu nu. It's a little bit egregious. You can write down the whole left-hand side about this, I think. The problem is that R mu nu, the Ricci tensor, and R, the curvature scalar, depend on the metric. Notice I didn't tell you what the dependence was. It's because it's kind of ugly. Here is one component of the Riemann tensor written in terms of the metric. So, even if I tell you what the metric is, just calculating this is work. But that's not your job. Your job is to solve for the metric in some situation of physical relevance. And it's just a god-awful mess with a lot of terms. And again, if you were my age, you would be writing down late into the night, hoping you did not write down a nu when you meant to write down a mu, and calculating all these things. So Einstein himself looked at his own equation and kind of laughed and said, of course, no one will ever solve this equation for any physically relevant situation. A couple of years later, Carl Schwarzschild did solve it. And the way he did it was just to make the right number of simplifying assumptions. Say, look, I don't care about the energy momentum tensor. Let me ask, what is the gravitational field, the curvature of space-time, outside the sun? So I'm outside the sun, so I'm in empty space. T mu nu is 0. Furthermore, I'm completely spherically symmetric, right? What's happening in one direction away from the sun will be the same as every other direction away from the sun. Furthermore, the sun isn't vibrating or anything, it's just sitting there statically. All of these assumptions let him simplify his life to the point where he could exactly solve Einstein's equation. And the result is this famous expression, the Schwarzschild metric, which is the unique curved space-time according to general relativity outside a spherically symmetric mass distribution. And you see what I mean by a solution to Einstein's equation is a metric tensor. G mu nu, tell me what all the coefficients are. And furthermore, they're not that wacky. They're a little bit wacky because we're now working in spherical coordinates. So you notice that this r squared sine squared theta, these are not because space has gone crazy, it's just because we've changed coordinates to be spherical coordinates rather than rectangular coordinates. That is appropriate for the problem. All of the effort is in these upper two components. 1 minus 2gm over r, and minus 1 minus 2gm over r to the minus 1 power. This is the g00 and g11 coordinates, components of the metric tensor. Those are telling you things like the precession of the orbit of Mercury, or the gravitational redshift in the Earth's gravitational field. All of these predictions of general relativity are contained in here. And we can do just one little bit, we are nearing the end, don't worry, but one little tiny bit of thinking about this equation. You notice that if you look at these two components, G00 is 1 minus 2gm over r, GRR is minus blah, blah, blah over that. They blow up. When r equals 0, the G00 component is 1 minus infinity, because 2gm divided by r, as r goes to 0, goes to infinity. And also, when r goes to 2gm, when the distance equals that particular amount, that second component, when r equals 2gm, this is 1, this is 1 minus 1, this is 1 over 1 minus 1, which is 1 over 0, which is infinity. These are called singularities in the math literature, places where your expression goes to infinity, where it blows up. These are places where your first guess is something has gone terribly wrong. But people weren't sure about whether things were going terribly wrong. Does this mean that relativity is wrong, or is this just some mathematical artifact or whatever? And because the universe always likes to keep us on our toes, the answer is different for the two places. There are two places where there's a singularity. R equals 2gm, R equals 0. R equals 2gm is completely fine. There's nothing wrong with it. You've just chosen bad coordinates in which to express space-time. R equals 0 is a true singularity. The curvature of space-time is going to infinity. Most people believe that an eventual theory of quantum gravity will make everything okay, but we don't have that theory yet, so we don't know. But that point at r equals 2gm turns out to be something we know and love. It is the event horizon of a black hole. And you can kind of get a feeling for what's going on by thinking about the 0,0 component, because we told you what that is. That's the rate of your personal experience of time flowing with respect to the time coordinate you've chosen in the background, right? And this number, the rate at which you experience time flowing compared to the coordinate, goes to 0 at this location, r equals 2gm. So we've plotted it here. Far away, at r equals infinity, this is 1 minus 0, that's just 1. That just means space-time is flat. There's no gravity. You're far away from the object. But as you go in to smaller and smaller distances, you hit a point where time, from the point of view of an outside observer, seems to stop flowing. That sounds bad. We now know what it is. It is the event horizon of a black hole. Neither Schwarzschild nor Einstein got this. They went to their graves not knowing that there was something called a black hole. It took decades for physicists to figure out that this is not a mathematical artifact. This is real. We can take pictures of them now. This is a picture of a black hole from the Event Horizon Telescope. You're not seeing the black hole, you're seeing its effect on the light behind it, but it is clear evidence that the black hole really is there. So this is the final lesson of the talk, which we started with, which is that the equations are much smarter than we are. This is why the equations matter. This is why you take the effort to understand what's going on, because it wasn't just black holes that were implicit in this equation, even though we didn't know it. gravitational waves, the growth of large-scale structure in the universe, the expansion of space itself, our ability to detect dark matter via gravitational lensing, they're all secretly living inside Einstein's equation. It's taking us a long time to figure them out, but the equation knew it all along. That's why it's worth it on our side to put a little bit of effort into understanding what that equation is trying to tell us. Thank you very much.
Do we have to know all that for the exam?
Oh, yes.
Okay. So we have time for some questions. Please form lines at the microphones on the side, or feel free to raise your hand and someone with a microphone will find you. Question over here.
Hi there. Just wanted to say thank you for a wonderful talk. That was really awesome. And beyond that, this is more of a general question. Sure. We were talking about the unification of these theories between gravity and the standard model and this. And I just was wondering what you thought about the Wolfram Physics project and the idea that we can see the universe through these like hypergraphs, and that I was just wondering because it's like elegant in a way that physics hasn't been in a very long time. And that's it. Thank you.
Good. So for those of you who are not familiar, Stephen Wolfram, who is the inventor of the Mathematica programming language among various papers in physics, has a new program to reconstitute all of physics based on discrete cellular automata or generalizations thereof that he calls hypergraphs. I'm rooting for him. I think it's great that he's trying to be that ambitious. I think that my personal credence that he will eventually succeed is pretty low. Basically, what he's trying to do is to say, if the ultimate laws of physics are really going to be simple, I can just guess them. I don't need to look at the world and do any experiments. There's only a small number of simple things that can happen. And he's very comfortable living in a world of discrete cellular kind of structures. But to me, what we do know about the world is very different than his starting point, especially because one of the things, whether it's relativity or Newtonian mechanics or quantum mechanics, one of the things that we know about the world is that, or seem to know, is that it is reversible. The fundamental laws of physics do not tell the difference between past and future in any fundamental way, whereas Wolfram's rules absolutely do tell the difference between past and future. So I think that either he will find out that his proposed rule reproduces all of quantum mechanics in some way, in which case, why not just begin with quantum mechanics? Or it disagrees with quantum mechanics in some way, in which I bet it's ruled out by data. But we'll have to wait and see, because we don't know the answers yet. Just keep talking, it usually turns on.
Hi. I'm curious about Hawking radiation. So I imagine that it's hiding somewhere in there. I was curious where.
Oh, good. Hawking radiation totally not hiding in here anywhere, because Hawking radiation comes about through quantum mechanics. And this equation and everything I talked about in this talk is entirely classical. Now, just like Einstein was faced with this puzzle in 1905, how do I incorporate gravity into my new framework? Now we're faced with the puzzle, how do I incorporate general relativity into the quantum mechanical framework? We do not have the final answer to that one yet. Some of us have ideas, different people have different favorite categories, but what we can do in the meantime is say, well, what if space-time is classical, but the stuff that lives on space-time is quantum mechanical? That framework is where Stephen Hawking derives the existence of Hawking radiation. So Hawking radiation comes from quantum fields living on a classical background space-time. We are trying very hard, and there have been real successes in promoting that to an approach that is quantum from the start, but we don't have the final answers yet.
Thank you.
Go ahead.
Hi. So I don't know a ton about physics, but I really like it. Found this really interesting, and I appreciated it. And I had an astronomy professor a few semesters ago who told me about this thing called MOND. And it sounded really interesting, and it sounded like it had a lot of potential to explain some things in a different or useful way. And I was just curious what your thoughts were on MOND.
What are you teaching students here at the University of Michigan?
It wasn't here. It was at WCC, actually.
Oh, now I get it. Okay, good. No, there is a very natural thing to ask yourself. This picture that you have in the bottom right corner, this is literally a reconstruction of where the dark matter has to be to understand the gravitational lensing that we observe in the universe. So exactly because gravity is universal, exactly because everything interacts with gravity, gravity gives us a way to figure out how much stuff there is in the universe. Because if there's stuff, it leads to a gravitational field. So you do that. You look at a galaxy or a cluster of galaxies or a large-scale structure, you find over and over again that the implied amount of stuff you need to account for the gravity is more stuff than you see. And the word see is very general here, and we can get into that if you want. So astronomers posit the existence of invisible matter called dark matter, and that fits the data enormously well. But there is another obvious thing to consider, which is maybe general relativity, Einstein's equation right here, as successful as it is, maybe it's wrong. Maybe it fails in some subtle and intricate way when you apply it to galaxies or clusters of galaxies or whatever. So MOND, modified Newtonian dynamics, is an example of this. We try to change the basic rules, do away with dark matter, and explain the dynamics of the universe without any new stuff. So I'll be very blunt. I think it doesn't work. It doesn't work for a couple of reasons. Number one, theoretically, it's much uglier than just presuming dark matter. Look, in some sense, the air in this room is dark matter. I can't see it, but I know it's there because I can feel it when I wave my hands. That's exactly what's going on in this picture. This is a reconstruction of the forces due to gravity caused by dark matter. Having dark matter is not a big leap away from known physics. But more importantly, the original motivation for modified Newtonian dynamics was to explain the dark matter seen in individual galaxies. And they invented the theory to do that very well. It does that very well. But when you try to go past individual galaxies to clusters of galaxies or to the cosmic background radiation, it fails. In fact, the modern proponents of MOND also have dark matter in their theories to account for those as well. So in my mind, why not just have dark matter and stick with Einstein's theory?
I know it's just a lot less, but thank you for answering the question.
Look, let me say one final thing. I wish it had been right. As a theorist working in cosmology and gravity, nothing would be cooler than if gravity were wrong cosmologically. I am responsible for various papers suggesting that. I just don't think the data is pointing in that direction.
Hi, thank you for such a wonderful talk. I just had a quick question for you about, I see that pi shows up in
Yes.
Einstein's equations. And yeah, I know whenever pi shows up, there's a circle hiding somewhere. I don't know if you have any simple intuition about why pi shows up in this equation or not, but
100%. So you know that Einstein's birthday and Pi Day are the same day.
True.
March 14th. That's not why, though, but if you Google why does pi show up in Einstein's equation, you will find a blog post of mine where I explain it. It's not Einstein's fault. It's Newton's fault that pi shows up in Einstein's equation. Because remember, G, Newton's constant, showed up in Newton's equation for gravity. But Newton's equation is the answer to the question. I have 2 points with masses. How much gravity is there between them? It turns out that is not the most elegant way of thinking about gravity. Rather than having a force directly between two objects like Newton had, it's better to think of a field filling all of space and being affected by the 2 points. This is a way that, forget about general relativity, you can reformulate Newton's law of gravity in a field theory language by imagining a gravitational field filling all the Earth, filling all of space. But then instead of saying I have a point here and one other point there, now you're saying I have a point here and a sphere around it that is pulling in all directions. So when Pierre-Simon Laplace reformulated Newtonian gravity in the language of field theory, the equation is not F equals G mm over r squared. It's grad squared phi equals 4 pi g times rho. And it's that pi going from 2 points pulling on each other to a field being influenced that also shows up in Einstein's equation.
Thank you so much.
I'm going to go back and forth.
I really enjoyed the talk. Thank you. I hope I'm not getting too into the weeds here, but been very interested in this idea that you've worked on that spacetime can sort of be an emergent property from entropy, and that you can sort of decompose, say, a Hilbert space into factors, and the mutual information between factors tells you about the spacetime interval between them. And this feels like a very exciting sort of fundamental idea. I was wondering if you have any foresight about where this is going, and if you could explain things like inflation with it.
We are all about the weeds. You've come to the right place. Our garden is full of flourishing weeds that we can get into. Yes, so as you will see in the last 5 minutes of the talk that I will give tomorrow morning, as lovely as Einstein's equation is, and as beautiful as this theory is, what my research these days is more quantum mechanically based. And I think, the way that I think about it is, quantum mechanics is a much more revolutionary, dramatic theory than relativity was. Relativity takes space and time and glues them together and gives them a geometry. Quantum mechanics says, no, there's not even any such thing as space. Time we can debate about. But space is somehow an approximation, an emergence that comes out of a deeper underlying quantum mechanical structure. If I go off-piste a little bit here, I would argue that physicists have not thought deeply enough about this fact because they are averse to thinking too hard about the foundations of quantum mechanics, which is too bad for the field of physics. Awesome for me because it means I can think about it and I don't have any competition thinking about it. So my grad students and postdocs and I have, for the last few years, been pursuing a program where you start with bare bones quantum mechanics and you ask how can space-time and gravity emerge from them? And we have some tentative, positive, promising results, but we're not anywhere close to even being respectable, much less finished. As far as inflation is concerned, no, I have no good ideas there. My current interests are more trying to just match the successes of the standard models of gravity and particle physics, and also to look for little tiny changes to them, little tiny violations of cherished principles like Lorentz invariance and locality that might be experimentally accessible, which would be really fun.
So my question was about, so it seems like in your talk, a lot of the innovations in a concept came from like these generalizations where like in geometry, they're like, oh, it's just parallel lines. And they're like, oh, it could go spherical or hyperbolic. And even with space-time, it was like Pythagoras theorem. And now, hey, we can add time to it and whatever. But when you're doing theoretical work as a theoretical scientist yourself, how do you know the generalization you're picking, or like when you're like, you're kind of, at least in the beginning, making it up.
Yeah.
Right? It could be t square and r cube for all you know. So
Right.
how do you know, how do you as a scientist like have a sense of, oh, this is an interesting generalization or direction to go down and this is not meaningful, and or is it just someone does an experiment and that's the only way to know?
So that's an excellent question. The dirty little secret is there's a whole bunch of wrong guesses that I didn't tell you about. I got to clean everything up and tell you only the right guesses along the way. So yes, of course, when you're actually in the process of developing these ideas, not only are you conjecturing or hypothesizing, but the vast majority of your conjectures and hypotheses are just wrong and are left on the cutting room floor. Some people empirically seem to be better at making these guesses than others, and one wonders how that is. And I think that things like dark matter versus modified gravity, or things like the interpretations of quantum mechanics. These are examples where we don't know what the final theory is. We don't know what the right answer is yet. So there are respectable, very smart people who deeply disagree. And even though they know we don't know what the final answer is, they strongly think that they're pretty close to the final answer, and you should listen to them, even though they disagree with each other. And the reasons they disagree come down to all sorts of different factors. What has worked for them in the past? Their own personality types. Are they more mathy or more down and dirty? Are they more space-time oriented or quantum oriented? There's a whole bunch of accidents of history that can give individual theoretical physicists different inclinations for how to take the current model and move beyond it. I'm a super strong believer that we need a multiplicity of approaches because, Einstein, the classic example, nobody was better than Einstein in the first 20 years of the 20th century at doing physics. But by the 30s and 40s, other people were better. And Einstein didn't become dumber. He understood quantum mechanics better than anybody, but his particular intuition for what to do next turned out to be less promising, less fruitful than other people's did. But I would still hire him, put him on the faculty, give him tenure. And I think that these days, when we have a whole bunch of theories, whether it's gravity or particle physics or cosmology, where the theories fit the data, but we still are trying to move beyond them, the data are not pointing us clearly in what is the right direction, I think we don't do a good enough job in taking diverse approaches to these questions, because instead of the data saying do this or do that, we have people saying, I think we should do this, and then persuasive people tend to win and things like that. And so it's very hard to figure out how academia as a whole should diversify its portfolio, but I think it should try a little bit harder than it does.
Thank you.
Hello, thank you so much for the lecture. That was fantastic. I had a question about Schwarzschild's attempt to solve the Einstein equation. In the region between the event horizon and the singularity, G00 is less than 0, which means
Yes.
the rate at which time flows relative to outside observers is negative.
Yeah.
How do we reconcile that with our intuitions on causality and even things like the arrow of time? Does that make sense?
Yes, I love this question because I know the answer to it. You are correct. If you look carefully for values of R, let's say R equals 1 times GM, right? Then this upper left corner is 1 minus 2, which is minus 1. That's a negative number. But look at the next one. Look at GRR, right? That's minus 1 over minus 1. So now that number has become plus. So both of these numbers flipped sign at exactly the same place. So it is not that space-time somehow went weird. It's that our coordinates on space-time are not telling us what we thought they were telling us. Inside the black hole, inside the event horizon, the coordinate that you and I have labeled T is now a space-like coordinate, not a time-like coordinate. The coordinate that you and I have labeled R is now the time-like coordinate. So if you ever teach general relativity, someday you'll grow up, become a faculty member, teach general relativity, and the day that you get to teach your students that R equals 0, the singularity inside the black hole, is not to your left, it's to your future. And the reason why you have to hit it when you're inside the black hole is the same reason you have to hit tomorrow. This will be a very rewarding day as a professor. They love that. They eat it up. But it's just a failure of our coordinates, not a truly physically weird thing.
I'm eating it up right now, so
Good.
thank you so much. That was great.
Thank you. I loved your talk. I had a quick question. So I guess from my understanding of the history of physics, before they understood why the orbit of Mercury precessed, they hypothesized a hypothetical planet, Vulcan, that would kind of correct for that gravitational anomaly. But then when they discovered the Einstein equation, that gravitational anomaly was explained by that new equation.
Yeah.
What's the difference between dark matter being that kind of like corrective Vulcan planet force instead of there possibly being a new equation that doesn't need dark matter?
Good. This is a very good question. But remember to tell the story slightly more fully. Before they hypothesized Vulcan as a new planet in the center of the solar system, they hypothesized a planet called Neptune at the outer edge of the solar system because the motion of the outer planets like Jupiter and Saturn and Uranus didn't fit with the predictions of Newtonian mechanics. So they hypothesized a dark matter planet, a planet that we hadn't seen yet. And it was discovered. It was there. They were correct. Then they tried the same trick in the inner solar system to explain the theory, the motion of Mercury, and it was wrong. They failed. You needed a new theory of gravity. But in retrospect, that arrangement where the far away thing needed new matter and the close by thing involved a new theory of gravity makes sense. As a general feature of field theory, we expect field theories that work in one regime to keep working as distances get bigger and bigger, but maybe to fail as distances get smaller. This is just a feature of how fields work in the world. So if a theory of gravity is going to fail, we would expect it to fail when gravity is strong and nearby. In the solar system, that's near the sun. That's why we're super interested in pictures like this one, where you're collecting data near the event horizon of a black hole. Because even though general relativity is probably right near black holes, it is very plausible that it's not quite. Whereas when you go to cosmology or the galaxy or things like that, it's really hard. And I've tried to invent a compelling field theory that matches gravity in the solar system but gives you something different far away.
Thank you.
I have a kind of a dumb question, and great talk. I have a lot of reading to do. But if the shape of space is spherical, or the saddle, the hyperbolic, the saddle shape, if to figure out that that's the shape of it, you're saying you take a measurement farther away from where you have your right angles. When it's actually space-time that has the shape, does the ruler change as you move along that surface? I mean, a yardstick doesn't change at the equator at the pole, but if space-time has the curvature, will the yardstick itself shape, and that'll make it difficult to make the measurement that you're trying to do in the first place?
Well, yes, so you have to be clever. Happily, we have a whole bunch of clever people working on this exact problem. So there's a whole set of very technical papers devoted to the question of what are the observable quantities that you confront when you have a curved space-time and you don't know how it's curved very far away. It turns out, for example, that shooting out two light rays and watching if they converge or diverge, not actually very practical for various reasons. But there's another thing we can say about these different kinds of curvature, which is that on a sphere, you can take the angles inside a triangle. Oof, I gave you a lot of stuff, didn't I? The angles inside a triangle on a sphere add up to greater than 180 degrees. On a potato chip, they add up to less than 180 degrees. That's something we can actually measure in cosmology. The cosmic microwave background gives us a triangle and a way to measure the angles between them. And it turns out that space is pretty close to flat. But basically all I'm telling you is, yes, we worry about this problem a lot, but it is one that we can address.
Great to meet you, Dr. Carroll. I have a question about black hole information paradox. I know there's been lots of attempts to solve the problem. Which one do you like the best? Which one do you think has most future?
I'm beginning to think that some of you folks have gone to lectures other than mine, because I didn't mention the black hole information loss paradox, but that's okay. Once you do, remember we had a question about Stephen Hawking and Hawking radiation, and that is derived in the context of putting quantum field theory in the background of this black hole space-time. But of course, we want everything to be consistent at the end of the day. So what Hawking showed is that a black hole has a temperature. It gives off radiation. But if it gives off radiation, it has to shrink because the energy from the black hole goes into the radiation. And so if you have something that contains information, such as my book, The Biggest Ideas in the Universe, if you have that and you throw it into a black hole, apparently to you, the information is now inaccessible, right? It's in the black hole. But Hawking says that black hole will eventually radiate away. The information contained in that book, in principle, we believe, although we don't know exactly, but we believe the information contained in the book should be encoded in detailed features of the radiation being given off by the black hole, because we think that information is conserved according to the laws of physics. Now, we don't know how that happens. That's what's called the black hole information loss puzzle or paradox. It's not a paradox, but it is a puzzle. In some sense, it's wholly unsurprising that we don't know why that happens, because it involves quantum mechanics and gravity at the same time. And those are two things that are notoriously difficult to put together. The reason why it is nevertheless vexing is because there are very good arguments that we shouldn't need details of quantum gravity in order to solve this puzzle, but apparently we do. This is just yet another reminder that quantum gravity is a big challenge. It is fundamentally a different kind of thing than other quantum mechanical theories that we have. So I'm not going to answer your question. I know your question is, what is my favorite approach to it? I am very impressed with a number of steps forward that have been taken over the last 5 and 10 years of people working with either string theory or string theory inspired models, ADS, CFT, and things like that, to at least construct some examples of explicit models where black holes seem to evaporate and information is preserved. But there's a lot of subtleties here, and I still think that people aren't taking quantum mechanics itself quite as seriously as they should. So I'm going to remain silent on what I think the final answer actually is. But let me say one fact, one opinion that might matter here, which is that from my point of view, where quantum mechanics is the central thing and space-time is just an emergent approximation, the arguments that make the black hole information loss paradox so puzzling become a little bit less forceful, because they always put space-time front and center into defining what you mean by this paradox. So I think the door is still open for some reimagination of what the paradox is, based from a purely quantum mechanical framework in which we all go, that shouldn't have been a puzzle ever.
Time for about 2 more questions, starting over here.
Thank you, Dr. Carroll, for the talk. So my question was, now that we know a little bit about Einstein's equations, could you clarify exactly at what point they start to fail in quantum mechanical senses, and try to connect that to your idea of challenging fundamentals? Does challenging fundamentals involve just quantum gravity and string theory, or is there more on that scene?
That's another great question. I mean, you're doing okay with the questions here, I gotta say. Of course, we don't know for sure where it breaks down. There's 2 things to say. One is, we do have a kind of a rough guess as to where you would expect the classical theory of general relativity to break down, which is namely when the curvature of space-time, if you go back into the Riemann tensor and its definition, the curvature of space-time has units of 1 over length squared. It's basically the radius of curvature of whatever you're looking at. So if that length scale is infinity, you're in flat space. If it's more and more curved, then you're in more and more curved space. And there's something called the Planck length. This is a fundamental length you can make just by numerology, playing with Planck's constant and Newton's constant and the speed of light. And when the radius of curvature of space-time becomes of order the Planck length, that's when you would expect quantum gravity to become very, very important. Now, compared to a black hole, you might think, well, black holes, gravity is strong, maybe quantum gravity is important near the event horizon, but the curvature scale of space-time is way, way smaller than the Planck scale near the event horizon of a black hole. So your first guess is that even black holes should show no important breakdown of classical physics. Your second guess is to remember that there's something called the black hole information loss paradox, and that seems to be telling us that something about classical general relativity is breaking down way before you reach the Planck scale. And that's what makes it so challenging. There seems to be some fundamental breakdown of locality, of the idea that the world is made of different points of space-time interacting with only their nearest neighbors. And that's something that we're still trying to wrap our heads around. Last question. Better be good.
Hello, can you hear me? So it's a kind of general question. So one takeaway of your talk for me was that sometimes very fundamental features of our scientific understanding of the world can change. So for example, abandoning Euclidean space and time. So given this, I wonder if you have any thoughts about how to set credences in the basic features of our current physical theories changing or sticking around in a future theory of everything.
I'm glad we have another hour for me to explain this one, right? So I don't want to keep anyone. There is a feature of, there's two different ways in which a scientific theory can be overthrown and replaced with a different scientific theory. One is you realize the previous theory was just wrong. Copernicus was better than Ptolemy. Like Ptolemy, actually, there's no regime in which Ptolemy is the right approximation to the world, right? But as we become better at doing physics, more and more often, not always, but more and more often, we find situations where the new, better theory still contains the old theory, but in some approximation. So Newtonian mechanics is an approximation to relativity. Classical physics is an approximation to quantum mechanics and things like that. Maxwell's equations are an approximation to quantum electrodynamics. And so in those cases, for the philosophy buffs in the room, there's an idea called structural realism, that what we're discovering when we do physics is not the ontology of the world, is not the stuff the world is made of, because who knows that tomorrow we won't have a different idea of what, maybe Wolfram is right, the stuff that the world is made of is completely different. But there are structures within that stuff that persist from theory to theory. And so when you talk about the credences of these theories, general relativity, the standard model of particle physics, etc., my credence that they are themselves the once and for all theories are very small. But my credence that some version of them will remain true as an approximation to a better theory are very large. The fun part is, can we imagine some subtle difference in the fundamental theory that has some kind of unanticipated manifestation in the theories we know about? We have puzzles. Why is there more matter than antimatter? Why did the early universe have low entropy? Why is the Higgs boson so light? Why is the cosmological constant so small? We have good arguments. How does information come out of black holes? The thing about all these puzzles is there are reasons to believe that they should be addressable in physics that we kind of understand, but the attempts to do so are not very good. Maybe there's something deep underlying all of this stuff that will ultimately play a crucial role in understanding those things. I can't put a high credence on that in any one of those cases, but it's what I spend my life doing, so clearly I have some credence in it. Thank you very much.